Well, students, in the last lecture, we have started proving the convergence theorem of secant method. Let us continue our proof in this lecture. Let us quickly recall the statement of the secant method. We assume that f is a C2 function and the root that we are interested in capturing through secant method is a simple root. It means f dash of r is not equal to 0. If we assume these two conditions, then we can find a delta neighborhood of the simple root r such that if we start our initial guesses x0 and x1 in this delta neighborhood, then the theorem says that all the terms in the secant method iterative sequence are well defined, and also each member of the sequence belongs to the delta neighborhood of R. And finally, the theorem also concludes that the sequence xn converges to R as n tends to infinity. Further, the theorem also says that the order of convergence of the secant method is 1.62 approximately. To prove this theorem, we have first established an expression where we can find two parameters xi n and eta n for each given n is equal to 2, 3 and so on, such that this expression holds. We have derived this expression, and now let us proceed to prove the conclusions of the theorem using this expression. Recall that we have assumed the root of our interest r is a simple root, and also we have assumed that f is C2 function. Therefore, in particular, f dash is a continuous function. With the help of these two assumptions, we can find a small neighborhood of the simple root r such that f dash of xi is not equal to 0 for all xi belonging to this delta neighborhood. This is a well-known result in basic analysis. Note that this is not the delta neighborhood that we want in our statement. If you recall, in our statement, we want a delta neighborhood of R in which we want to choose our x0 and x1, right? What I'm trying to say is that this is not the delta neighborhood that we are looking for. In fact, we should choose a delta less than this delta naught in some way. Let us see how to choose this delta. Let us introduce two notations. We will always use the notation small m to denote the minimum of f dash of xi modulus for all xi in our delta neighborhood of R. Note that we have not chosen our delta yet, but I am just introducing some notations here, and we will choose our suitable delta little later. And capital M is the maximum of the modulus of f dash of zeta for all zeta in our delta neighborhood where f dash is non-zero. Since f dash is non-zero in this interval, we can see that small m is always non-zero. And also, without loss of generality, we can assume that the capital M is also non-zero. Why? If capital M is 0, it means f double dash of zeta is equal to 0 for all zeta in the delta neighborhood, right? That implies that f dash is constant and in this neighborhood, and that implies that the graph of the function f is a straight line in this interval. If that is so, you can see that your secant method will in fact exactly capture the root r, and there is nothing else to prove for the convergence, right? Therefore, we can assume without loss of generality that m is strictly greater than 0, in which case we need to prove something, whereas in this case, everything becomes trivial and there is nothing to prove. As I told, this neighborhood is what we are interested in, and we are yet to obtain the delta precisely. Assume that x0 is not equal to x1 is not equal to r, and also choose x0 and x1 sufficiently close to r such that the parameter epsilon, which is defined by this expression, is less than 1. We can always choose this. Well, the largest delta less than delta naught, which makes this epsilon less than 1, is the required delta for us. Well, why we are interested particularly in this type of expression, we will come to know this in the next step. Recall that we have derived this expression as the first step of the proof. From here, you can see that mod xn plus 1 minus r into minimum of modulus of f dash of psi, which we denote by m, is always less than or equal to mod xn plus 1 minus r into f dash of psi n, right? And that is equal to 1 by 2 mod xn minus 1 minus r into xn minus r into modulus of f double dash of zeta, and that is less than or equal to 1 by 2 into this expression xn minus 1 minus r into xn minus r into capital M, because capital M is maximum over all these numbers, right? Therefore, we can see that mod xn plus 1 minus r is less than or equal to m by 2 small m into xn minus 1 minus r into xn minus r. This will hold for all n equal to 2, 3 and so on, because this expression holds for all n equal to 2, 3 and so on, right? Now you can understand why I have involved an expression like m by 2m into x0 minus r and so on in defining the parameter epsilon, because such expressions are sitting on the right hand side of my error term. Remember, this term is the error involved in xn plus 1 when compared to the root that we are interested in. That is why we chose our x0 and x1 in this way. Well, since the choice of x0 and x1 are in our hand, theoretically we can do this, but practically, of course, we do not know, or therefore we cannot do it. But however, this is a theoretical result to make sure that the secant method indeed converges under certain hypothesis. Okay, so now we understood how this inequality is coming. Let us take n equal to 1 in that inequality. We get mod xn plus 1 minus r. Since we have taken n equal to 1, it is mod x2 minus r is less than or equal to m by 2m times mod xn minus 1 minus r, that is x0 minus r, into mod xn minus r, that is x1 minus r. Now I'm just conveniently using my information. Here I'm using the fact that this term is less than or equal to epsilon, and this term, since I have chosen x1 from the delta neighborhood of r and it is pretty close to r, in fact you can put here less than or equal to, and that gives me epsilon into delta. Since x0 and x1 are chosen in such a way that epsilon is strictly less than 1, therefore epsilon into delta is strictly less than delta. That shows that x2 also belongs to our delta neighborhood of r. Now you can use an induction argument to show that all xn's belong to the delta neighborhood of r. all we have to make sure is that our x0 and x1, which are chosen in the delta neighborhood, should be carefully chosen such that this expression is less than 1, right? That is used here. Once you make sure about your initial guesses, then your entire sequence will sit in the delta neighborhood. That is what we have shown here. Let us go back to the statement of the theorem and see that this is in fact one of the statement that we have to prove as a part of the theorem, and that we have proved now. Once you prove this, the first conclusion is also easy. It follows immediately from the inequalities that we have obtained. Recall that this neighborhood is chosen so that f dash of xi is not equal to 0 for all xi in this neighborhood, right? That implies f is strictly monotonic in this interval. That means f of xn is not equal to f of xn minus 1 for all n. Why? Because all xn's now belongs to our delta neighborhood. That is what we have already proved. And in this delta neighborhood, f is strictly monotonic. Therefore, this happens, and that precisely means that your sequence is well defined, because we have seen from the expression of secant method that xn is not well defined, means at some n we come across the situation that f of xn is equal to f of xn minus 1, right? And that can never happen provided our initial guesses x0 and x1 are taken from this delta neighborhood, and therefore the conclusion 1 is also proved. Let us now prove the main conclusion, that is the sequence xn converges to R. To prove the convergence, first observe this inequality. How will you get this? Well, again, in the last slide, we have obtained this. Now, I am just multiplying m by 2m on the left hand side. Therefore, the right hand side will have m by 2m square, right? That is what precisely I am writing here. On the left hand side, I have multiplied this quantity. Therefore, the right hand side already has this quantity. Now, one more m by 2m comes. Therefore, you have square. Now, if you recall how epsilon is defined, you can see that the right hand side is further less than or equal to epsilon square. Again, go back to this expression. Now take n is equal to 2 here, and thereby you will have x3 minus r is less than or equal to m by 2m into mod x 2 minus r into mod x1 minus r, right? So the same idea, I am taking modulus on both sides and using this notation. That gives me this expression. Well, you have two terms here because I have multiplied m by 2m on the left hand side, and therefore I have one more extra term m by 2m on the right hand side. Now you see this is less than or equal to epsilon, and this term we have just proved here that this is less than or equal to epsilon square. Therefore, this entire right hand side is less than or equal to epsilon into epsilon square, that is epsilon cube. Now you follow the same idea, you get x4 case. You can see that m by 2m into x4 minus r is less than or equal to epsilon 5, and you proceed in the same way. In general, at any nth term, you will have m by 2m into modulus xn plus 1 minus r is less than or equal to epsilon times the number qn plus 1. And what is this number? Well, let us carefully observe. Before that, we had epsilon, because we know that m by 2m into x naught minus r is less than or equal to epsilon, because epsilon was defined as maximum of this, as well as m into 2m into x1 minus r, right? Therefore, both these terms are less than or equal to epsilon. So, in the first term, we had q naught is equal to 1. In the second one, we had q1 is equal to 1 again. In the third case, we had q2 is equal to 2. That is the sum of these two terms is what we got as q2. And what is q3? Q3 is 3. That can be seen as sum of these two terms comes as q3, and q4 is 5. Again, you can see it as sum of these two terms. In that way, in general, qn plus 1 can be written as qn plus qn minus 1. The sum of the powers of epsilon in the immediate previous two cases, with the understanding that q0 equal to q1 equal to 1. Now, what can you say about this sequence qn? This is very familiar to all of us. What is this sequence? Well, this sequence qn is the well-known Fibonacci sequence of numbers, and we know that qn tends to infinity as n tends to infinity. Now you see this inequality. This is some non-zero finite quantity, so you can take it to the other side. This is the error involved in the n plus 1th term of your secant method iterative sequence when compared to the simple root r, and that error, let's call this as en plus 1 modulus, that is less than or equal to some constant times epsilon to the power of qn plus 1, and this number qn plus 1 tends to infinity as n tends to infinity, right? Also, we have chosen our initial guesses x0 and x1 such that epsilon was less than 1. Therefore, you can see that the right hand side goes to 0 as n tends to infinity. That is equivalent to saying that sequence xn tends to r as n tends to infinity. Therefore, we have proved the convergence of the secant method iterative sequence. Remember, to achieve this, we had three main hypotheses. One is f should be C2. Second, the root that we are interested is a simple root. And third is that we have to choose our initial guesses x0 and x1 in a neighborhood of R in which f dash never vanishes. If you make sure all these three hypotheses, then your secant method will converge. In fact, your secant method's iterative sequence will be well defined, and that sequence will sit in the delta neighborhood that we chose, and also the sequence will converge. All these three are achieved. Now there is only one conclusion needs to be proved, that is the order of convergence. Let us see how to prove the order of convergence. Recall from the definition of order of convergence, we say that a convergent sequence is said to converge with order alpha if there exists a constant c and a real number alpha such that xn plus 1 minus r is less than or equal to C times mod xn minus r to the power of alpha for sufficiently large n. If you recall, this definition is given in the chapter 1 of our course. In particular, in this proof, we will try to find the constants C and alpha such that limit n tends to infinity mod xn plus 1 minus r divided by mod xn minus r to the power of alpha is equal to C. Assume that without loss of generality, we have assumed that xn is not equal to r for all n, right? Therefore, we can equivalently look for C and alpha such that this condition holds. Then also we can claim that the sequence xn converges with order alpha. Let us see how to find C and alpha such that this condition holds. Again, we will start with the expression that we have derived as the first step of our proof. This expression can be equivalently written like this. We have taken these two terms on the left hand side and this term on the right hand side. That's all we did. Now take modulus on both sides and divide both sides by mod xn minus r to the power of alpha and take this term to the right hand side. Well, I could have kept this on the right hand side itself. So finally we get mod xn plus 1 minus r divided by mod xn minus r to the power of alpha is equal to mod f double dash of zeta n by 2 f dash of zeta n into mod xn minus 1 minus r into mod xn minus r to the power of 1 minus alpha, because we have divided the right hand side also by mod xn minus r to the power of alpha. Therefore, we got this power here because already we have one term in the numerator, right? So this is a very simple manipulation from the expression that we have derived. And what is that term that we have multiplied both sides? Well, it has this number alpha, which we will have to find appropriately such that we get this expression for our secant method iterative sequence, right? So we have to keep this in mind and go ahead. Let us see what to do with this expression. In fact, we can further manipulate this term conveniently. How to do that? Well, I can write the term in this form also. If you recall, we had mod xn minus r into mod xn minus 1 minus r, and there was a 1 minus alpha power in xn minus r, right? That is what we had here, and that I'm writing in this form. Now you can see that this is nothing but xn minus r to the power of beta. Therefore, my beta should be 1 minus epsilon in order to match these two terms, right? And this term is nothing but mod xn minus 1 minus r to the power of minus alpha into beta, right? That is what I'm writing, that alpha into beta should be equal to minus 1. So if I choose my beta and alpha in such a way that it satisfies these two equations, then this expression will match with this expression, right? And this expression is precisely what we have here, which is coming from our basic expression derived as a first step of our method. Remember, this expression is directly coming from the secant method iteration formula, right? Therefore, these parameters are chosen to match the formula of the secant method. Well, this immediately says that beta is equal to minus 1 by alpha, and that I will put here to get minus 1 by alpha is equal to 1 minus alpha, and that gives minus 1 is equal to alpha minus alpha square. or alpha square minus alpha minus 1 equal to 0. So that immediately gives me how I should choose my alpha. Yes, alpha should be chosen in such a way that it is a root of this quadratic equation. Well, it will have two roots. We want alpha to be a positive number. Therefore, we will choose the positive root of this quadratic equation, and that is given by alpha equal to 1 plus root 5 by 2, which is approximately equal to 1.62. If you go back to our theorem statement and see that our theorem was demanding that the order of convergence of the secant method is approximately 1.62, which is precisely root 5 plus 1 divided by 2. Well, the same number is also achieved in our calculation. Therefore, we are pretty close to the proof of the order of convergence, because we got this value alpha equal to 1 plus root 5 by 2. But we are still not done, because we have to match it with the expression here, because this will tell us that the alpha is indeed the order of convergence of the secant method. In that process, we have to also get what this C is, because the definition says that we have to find a C and a alpha. Well, we have found alpha. We have to also find what this C is. Let us go to do that. That should not be very difficult. You take limit on both sides of this expression. So you have limit n tends to infinity in each of these terms. You can see that this I want to be equal to C, right? That is what is demanded in my definition. And similarly, this should also be equal to C. You can observe that this term and this term are exactly same. Only thing is one index is less here. But that doesn't matter, because we are anyway taking limit n tending to infinity. Therefore, this should also be equal to C, right? And what about this term? When we take limit n tends to infinity, well, you go back to the Sandwich Theorem, which we stated in our first chapter. Remember, zeta n is taken between xn and xn minus 1. Of course, this is like if xn minus 1 is less than or equal to xn. Otherwise, it will be the other way around. And similarly, zeta n also lies between xn and xn minus 1. And we know that both these are tending to the root that we are interested in, that we have already proved. Since we have proved that, we can use the Sandwich Theorem to show that both zeta n also converges to R and xi n also converges to R, right? So once you see this, then we are through with what could be the limit of this term. Yes, the limit of this term is f double dash of R divided by 2 into f dash of R. Therefore, we have this equation in which we have decided to take this to be equal to C and this also equal to C. And you can see that C will satisfy this equation. A direct substitution shows that C is given by this. And recall, we have already obtained alpha as root 5 plus 1 divided by 2, which is approximately 1.62. So this is what precisely we want to show in the expression for order of convergence, and that we have achieved. Well, here we have alpha by alpha plus 1. That should not be a problem, because alpha satisfies this quadratic equation, right? Therefore, alpha square is alpha plus 1, or alpha is equal to alpha plus 1 by alpha. In our derivation, we got this term to the power of 1 by alpha, but I have given in the statement that it is alpha by alpha plus 1. That should not be a problem. And this completes the proof of the convergence theorem of secant method. You can see that secant method converges slightly faster than the linear convergence, and its order of convergence is a fractional number, right? Finally, let us give an example to show how to compute the terms of the iterative sequence of secant method. For this, let us take our usual equation, sin x plus x square minus 1 is equal to 0. If you recall, we have done this example both for bisection method and the regular falsy method. In both the cases, we have taken the interval 0 to 1. Now, let us take x0 equal to 0 and x1 equal to 1. Note that for secant method, we don't need to choose x0 and x1 on the either side of a root, but simply I am doing it here in order to see the performance of secant method when compared to the bisection method. Given x0 and x1, we have to find x2. Its formula is given by x1 minus f of x1 into x1 minus x0 divided by f of x1 minus f of x0, and that in my calculation is given by this number, that is 0.543044, and the error involved in x2 when compared to the root r is equal to 0.6367 and so on is given by this number. Similarly, you can find x3. Now what you have to do, you forget x0, use x1 and x2 to find x3, and the formula is given by x2 minus f of x2 into x2 minus x1 divided by f of x2 minus f of x1, and that is approximately given by this number. And similarly, we can find x4, and that is given by this. For this, you have to substitute the value of x2 and x3 in the formula, and for x5, you have to use x3 and x4 and so on.